In this video, we shall briefly discuss 2 points. The first point is how to perform tests of significance of the different effects present in the model, both fixed effects as well as random effects. Let us start with a model which has got only fixed effects. So we have already seen models of this type. Now suppose we are trying to test whether the input corresponding to the j index is significant or not. We shall couch this as this null hypothesis H0 where beta j's are all same. We have already seen how to perform such a test. Under H0 all the beta j's are constant and this constant may be merged with mu. So we get a null model consisting of only the intercept term and alphas. We fit both this full model as well as that null model without betas and we compare them using likelihood ratio test. We have already seen how to do that. However, if the beta j's are random effects, we have denoted them by bj and we have the corresponding distributional assumption on bj's, then in order to test whether the index j, that is the input corresponding to the index j, is significant or not, we cannot really test whether bj's are all same because bj's are no more parameters and a null hypothesis must always be couched using only parameters. The test that will achieve the same effect here will be to test something involving the sigma b square. So we shall test H0 sigma b square equal to 0 or not. However, if we are interested in testing whether the input corresponding to the index I is significant or not, then we can of course still test H0, alpha i's are all same. Now we shall see how we carry out these tests in presence of random effects. Even the test for fixed effects will not have the same distribution, the same null distribution as we saw in case of fixed effects model because the presence of the random effect has now made the distribution of the data much more complicated. A lot has been written about how to perform the tests in presence of random effects. And the only thing that has transpired is that such a test is by no means easy. The main problem is because now the distribution of the data is rather complicated with some correlated structures coming into play. So even if you are trying to test only for the fixed effect terms and you work out the likelihood ratio, its distribution is not a nice and simple F distribution. So that is the main problem. People have suggested various approximations and for that you need certain assumptions which are not often realistic. People have suggested alternative techniques not using likelihood ratio at all but certain ad hoc algebraic identity based techniques. But those things cannot be worked out in any complex problem. They are only for absolutely simple situations. So what has finally emerged is that if you have to carry out test of hypothesis in case of a mixed effects model, you go for the likelihood ratio test as before. However, do not rely on the distribution of the likelihood ratio as given by F distribution or based on any chi-square approximation. Instead, you go for parametric bootstrap. So let us see how to perform that parametric bootstrap. In step 1, what you shall do is simply fit both the null model as well as the full model. For any likelihood ratio test, you do that. Then you work out the likelihood ratio. So look at the likelihood that you get under the full model, that is, you apply MLE and you get the full model, the MLE under the full model, plug them in the likelihood function, you get the likelihood. Similarly, do it for the null model, take the ratio, you get LR, likelihood ratio. Now the question is, how do you check if this likelihood ratio is too high or too low? So you need to calibrate it with respect to the null distribution. And theoretically obtaining the null distribution is the difficult part of the case. Now what you do is you go for bootstrap. And this is done in the following way. You carry out a loop. In the loop, you do the following things. In step 1, you generate data from the fitted null model. So you already have fitted the null model and you generate data from this null model. Since you generate data from a fitted model, it is called a bootstrap. And since you have used the model, you are not doing it merely by resampling from the original data. That is why we call it parametric bootstrap. Now you obtain the likelihood ratio from the generated data. That is, for this generated data, you again fit the full model and null model and find the likelihood ratio. You carry out steps 1 and 2 for the data you generated in part 3a. Now you do it a large number of times. Suppose you do it 10,000 times. So at the end of step 3, you have got 10,000 values of likelihood ratio and one value of the likelihood ratio that you obtain in step 2. That is your observed likelihood ratio, and these are your generated likelihood ratios. Now what you do is you do step 4, which is basically compute the p-value as proportion of generated likelihood ratios that exceed the original likelihood ratios. So the 10,000 likelihood ratio values that you generated in step 3, they give you the behavior of the likelihood ratios under the null hypothesis. And you locate your observed likelihood ratio that you obtained in step 2 with respect to this thing, that you will look at how many of the generated likelihood ratios are even more extreme than the likelihood that you have actually seen. And if this proportion is large, you will say that your observed likelihood ratio is not that extreme. Many of those things already exceed that. So you will say that I am accepting the null hypothesis. If on the other hand this estimated p-value is small, say less than 5%, you will say that you are rejecting the null hypothesis. So this technique remains the most universally accepted way of carrying out a test in case of mixed effects model. The next topic that we are going to discuss is whether we can estimate the random effect coefficients. Now, this sounds like an oxymoron. If it is not even a parameter, it is something which is random, how can we estimate it? So we should better correct it by saying that we want to predict these coefficients. Now, still the question remains that we say we are using random effects because we are not interested in the specific values of these particular coefficients. These are something like a random sample that we generated from a large population of similar such coefficients. We had many villages. Out of that we chose some random 3 villages. So we are not interested in these 3 villages. So why should we ever care about predicting about these 3 villages? Anyone who is going to read the report in future will not care about these 3 specific villages. True. However, in animal husbandry, that is, people who care about how to improve, say, the milk production of cows, they like to have predictions of these things. So basically, the reason why they like this is this: you have got, say, different male cows and female cows, oxes and cows, and you mate them. You want to know whether the resulting calves are good with respect to some measure of health, and you want to link that up with the various properties of the ox that you use. Now, these oxes are chosen randomly, so random effect. However, the same oxes are going to be used for mating even in near future. So it is important to know if one particular ox produces better calves than another. So that is why people in animal husbandry care to predict these random effects. Now, how do you do that? In case of fixed effects, we had got blues, best linear unbiased estimators. So naturally, here we have a similar concept which is called a bloop, best linear unbiased predictor. So here is the definition. Suppose B is some random coefficient that we are trying to predict. Then L prime y, a linear function of y, L is a fixed thing, will be called a bloop, a best linear unbiased predictor for B if the natural definition variance of L prime y should be minimum, subject to the condition that this is an unbiased predictor of that. Now, had this been a parameter, unbiased would mean its expectation always equals that, but this being a random quantity, we have to put that also inside the expectation, and we'll say expectation of L prime y minus B is always equal to 0. Notice the identity that I am using. By this I mean whatever parameter values you choose, it will always be equal to 0. That plays the role of unbiased, and subject to that we want to minimize the variance. We call that a bloop. The question is how to find them. Now, finding bloops is not entirely easy. A statistician named Henderson came up with a set of equations by which you can find bloops under the following special model. So in this case, we are assuming that we have this typical random effects model, y equal to x beta plus zg, that is the random effect part, plus epsilon. G has this particular distribution, mean 0, variance sigma squared times g, epsilon 0 sigma squared times r, same sigma square in both cases, and the crucial assumption, which makes it look a bit unrealistic, is that you know both g and r completely, and they are PD matrices. So if you have this scenario, in that case, Henderson came up with a set of equations called Henderson's equations, solving which you can find both blues as well as bloops. remember, when we are working with blues, they may also change a little because we have a different distributional assumption. And these Henderson's equations take this following form, a pretty huge system that you solve for beta hat and g hat. And here is the right hand side. Now when you solve for the entire thing, you will get beta hat, which will be the blue of beta. And when you solve for this g, that will be blue. Now the proof of this is pretty complicated, and also I do not want you to cram this complicated equation. This is just for the sake of completeness of our lecture that I mentioned this. If you are interested in knowing how people arrive at these things or how loops are used in animal husbandry and places like that, I would suggest that you go through this particular paper. I shall provide a link of this paper from our class web page. That loop is a good thing. It's a pretty readable paper. This paper, the content of this paper is not part of the syllabus, but if you want to just learn more about loops, this is a good place to look into.